Hello, today I'll be talking about silicon carbide MOSFETs. This video will provide a general overview of their advantages and some of their real-world applications. Here are some advantages when we compare silicon carbide to the traditional silicon MOSFETs. So silicon carbide has a larger bandgap energy of 3.2 electron volts, while silicon has only 1.1. It also has a wider bandgap, which allows the MOSFET to tolerate higher temperatures and thus operating at much higher power levels. They also have a higher breakdown voltage and a low drain to source on resistance, which allows them to operate at higher voltages. This specific material has a higher thermal conductivity, which plays a significant role in cooling and heat dissipation. This means they have fewer cooling needs. Silicon carbide MOSFETs can operate at higher switching frequencies and have lower switching losses. Therefore, this reduces the size of components, thus the size of filters. Overall, silicon carbide MOSFETs are better in size, cost, and weight reduction. Next, I will talk about the applications of silicon carbide MOSFETs. So PV and solar systems on a utility scale tend to support power levels between 100 kilowatts and 1 megawatt. The latest trend connects the PV system to a battery in order to store any excess energy. This battery can also provide power to the grid in case solar panels are insufficient. The solar panels are connected to a DC to DC boost converter for the next stage. The output of the boost converter is called DC link voltage. The boost converter is associated with a term called maximum power point tracker, or MPPT. This is a technique to maximize power extraction and efficiency of power transfer. The maximum power point is the load characteristic that changes when the amount of sunlight varies. This way, the efficiency of the system is optimized because the load characteristic of the system changes to maintain the highest amount of power transfer. Next, there is a DC to AC inverter, which converts the DC power from the boost into AC power that can be accepted by the grid. Both the inverter and boost converter benefit from the use of silicon carbide MOSFETs. They improve on power efficiency at higher switching frequencies and can handle operations at higher temperatures. Therefore, it reduces the cost and size of the filters and the need for cooling components like heat sinks. Silicon carbide transistors can also be used in high voltage systems of electric vehicles. EVs contain a high voltage battery and a high voltage bus that is usually up to 400 volts. The traction inverter is what converts the DC power from the high voltage bus to drive the traction motor that moves the vehicle. This system also includes a DC to DC converter to regulate the voltage to meet the motor's needs. These converters must be able to withstand heat and vibrational stress from road conditions while handling high power and current. Again, silicon carbide MOSFETs improve the efficiency of traction systems because of their operation in higher switching frequencies and lower switching losses. They also reduce the size of filters and the need for heat sinks, thus making the vehicle lighter and better on mileage. So in conclusion, silicon carbide MOSFETs are more efficient because they can operate in higher temperatures and voltages. They have higher and better thermal conductivity for cooling and heat dissipation, and can operate at a higher switching frequency with lower switching losses. Additionally, they are growing popular and being used in applications like PV systems and electric vehicles. And this sums up the introductory video on silicon carbide MOSFETs. Thanks for watching.